Find the optimal planting plan. In this problem, a farmer has to decide how many acres of corn, lentils, and wheat to plant to maximize his profit in the growing season. The farmer is constrained by a finite quantity of land, water, and labor. Taking a closer look at the crops, we know the dollar amounts of sales, expenses, and profit per acre associated with planting each of the three crops. Needless to say, the numbers in this problem are made up. We notice planting corn is the most profitable, and planting wheat is the least profitable. The quantity of resources required to grow each crop are shown here. For this problem, the units of land will be in acres, and the units of water and labor will be a generic units. Planting 1 acre of corn will require 1 acre of land, 3.5 units of water, and 200 units of labor. Planting 1 acre of lentils will require 1 acre of land, 4.0 units of water, and 120 units of labor. Planting 1 acre of wheat will require 1 acre of land, 2.0 units of water, and 100 units of labor. The total quantity of land is 10 acres, and the total available water supply and total available labor supply are stochastic variables which have a known probability of occurrence. The expected quantities of available water and labor are defined by discrete probability distributions. For example, there is a 15% probability that there will be between 25 and 30 units of water available. There is a 60% probability that there will be between 1,400 and 1,800 units of labor available. We'll assign the variables BW and BL to the quantities of water and labor available. In this problem, the decision variables are the number of acres of corn, lentils, and wheat to plant, and assigned variables x1, x2, and x3, respectively. This is a stochastic optimization with recourse problem, because the farmer needs to decide how much of each crop to plant before knowing the quantity of available water and available labor. If we write out the constraints for land, water, and labor, we'll include the term S as a slack variable in case the resource is not completely utilized. And we'll include a penalty term, P, to serve as a surplus variable in case it turns out there are not enough resources to grow and sell the quantity of crops planted. In this equation, all variables x, s, and p are non-negative. The objective function is to maximize the total profit, z of x, which equals c transpose x minus e transpose p, where c represents the profit from 1 acre of crop sales, x represents the quantity of acres of each crop grown and sold, e represents the expense of planting and growing a crop, and p represents the quantity of crops lost due to insufficient resources. The profit and expense are in units of dollars per acre, and the crop quantities are in units of acres. As an example, if the farmer decides to plant 3 acres of corn, 3 acres of lentils, and 3 acres of wheat, and it turns out that there is 36.2 units of water available and 1,784 units of labor available, then there is no shortage of resources. In fact, there is a surplus of 1 acre of land, 7.7 units of water, and 524 units of labor for this planting plan and stochastic resource realization. The total profit from this scenario equals $39,000. However, if the farmer plants 3 acres of corn, 3 acres of lentils, and 3 acres of wheat, and it turns out that there is only 24.7 units of water available and 1,105 units of labor available, then there is still a surplus of 1 acre of land, but there's a shortage of 3.8 units of water and a shortage of 155 units of labor. How to best allocate the water and labor in order to maximize profits is a separate deterministic linear programming problem. In this particular example, it would be most cost efficient to farm 1.9 fewer acres of wheat than to cut back production and hence sales of corn or lentils. After this cutback, 2.9 acres of land and 35 units of labor would not be used to grow any crops. The total profit would be calculated out as the difference between the profit from crops sold, C transpose X, minus the expense of crops which died out due to insufficient resources, E transpose P. For this scenario, the total profit equals $27,600, much less than the $39,000 when more resources were available. In this last scenario, if the farmer had perfect foresight and knew there would be exactly 24.7 units of water and 1,105 units of the optimal planting plan would be to plant 3.83 acres of corn, 2.82 acres of lentils, and 0 acres of wheat. The total profit from this scenario would equal $35,488 and exemplifies the cost of having to make a decision without knowing the quantity of resources available. To solve this problem, we'll employ Monte Carlo simulation for multiple planting plans. By varying the quantity of corn, lentils, and wheat between 0 acres and 10 acres, using a step size or discretization of 0.5 acres, this will amount to 9,261 unique planting plans, or combinations of X1, X2, and X3. If we simulate each of the 9,261 planting plans one time, there will be 9,261 trials in the simulation. To begin, the quantities of X1, X2, and X3 in acres are entered. Then, the stochastic quantities of water supply and labor supply are generated based on their probability distribution functions. Next, the sales, penalty, and profit are calculated. In the second trial, 0.5 acres of wheat are planted. New stochastic variables are generated, and the sales, penalty, and profit are calculated. This process repeats for all 9,261 trials, or unique combinations of planting plans. Next, a table is created to determine which combinations of X1, X2, and X3 have the highest profit. The average profit of each planting, which falls within a certain range of corn, lentils, and wheat planted, is calculated. For example, on the first trial, where x1 equals 0, x2 equals 0, and x3 equals 0, this planting plan would fall in the range of 0 to 2 acres for corn, lentils, and wheat. And the average profit is updated, and the next planting plan is considered. For the first 5 planting plans, all fall in this first range, but the sixth planting plan has an x3 value of 2.5 acres, and is therefore in a different range for wheat planted. As an example, planting plan number 4,359 includes 4.5 acres of corn, 9.0 acres of lentils, and 5.5 acres of wheat. Planting plan 6,354 includes 7.0 acres of corn, 4.0 acres of lentils, and 5.5 acres of wheat. With 9,261 trials sorted into 64 ranges, each combination of ranges for corn, lentils, and wheat will include either 125, 150, 180, or 216 unique planting plans. The average value of each of the 64 ranges are ranked from 1 to 64. If we sort the list of ranges by descending average profit, we can identify which ranges of planting plans are most profitable. From these results, the top 2 ranges of planting plans are notably superior to the remaining 64. The combined range for these 2 ranges is 5 to 7 acres of corn, 0 to 4.5 acres of lentils, and between 0 and 2 acres of wheat. By reducing our search domain to these top 2 ranges of planting plans, the total number of planting plans reduces from 9,261 plans down to 250 plans, using a half-acre step size. For more precise results, the step size is spliced by a factor of 5, from 0.5 acres to 0.1 acres. This results in more than 20,000 possible planting plans. For this second iteration, using the smaller step size of 0.1 acres, all 20,286 combinations of x1, x2, and x3 are simulated. Stochastic variables for water supply and labor supply are generated, and the sales, penalty, and profit are calculated. The simulation is repeated for the second combination, and the third combination, and so on. For this second iteration, we'll average the total profit for similar planting plans using revised ranges for the areas of corn, lentils, and wheat planted. This way, each range will be the average of at least 275 unique planting plans, and at most 432 unique planting plans. Although 20,000 simulations may seem like overkill, the more trials in a stochastic Monte Carlo simulation, the greater the sample size, and the greater confidence the modeler has in the results. The average profit for all planting plans in each of the 64 ranges are calculated, and the first 6 ranges are shown here. As before, each range is assigned a rank, and the ranges are sorted from most profitable to least profitable. We notice the optimal planting plan falls within the range of 5.5 to 5.9 acres of corn, 2.3 to 3.3 acres of lentils, and between 0.5 to 0.9 acres of wheat. In a third iteration, the range narrows even further. If we again use a step size of 0.1 acres, but simulate 20 trials for every planting plan, we can find the optimal planting plan by averaging the profit of the 20 trials for each of the 275 planting plans in this iteration. After sorting the results, the planting plan with the highest average profit is to plant 5.9 acres of corn, 3.0 acres of lentils, and 0.5 acres of wheat, for an expected profit of $45,478. The second ranked planting plan would yield an expected profit of about $200 less than the first planting plan, and would include planting less corn, more lentils, and more wheat. When reviewing the possible solutions, the answer is C.